Swayam Prabha. Digital India. Educated India.
In the last lecture, we had looked at the basic principles of forecasting, and we had identified some of the major methods that are used for developing the demand forecast. In today's lecture, we are going to be talking about the analysis of time series and the development of forecasts based on the time series. Specifically, we are going to be talking about methods of correlation, regression, and time series decomposition as they are applied to forecasting the value of the demand. So, to begin with, let us try to recall what we mean by this common term generally known as correlation. We are all familiar with this term, and we know that correlation to some extent measures the degree of association between two variables or two series. This is a central concept which is used in forecasting, and therefore we must clearly understand the distinction between correlation and regression. Correlation examines if there is an association between two variables, and if so, to what extent. So that is what the correlation coefficient measures, the degree of association between two variables, if at all there is any. And regression, on the contrary, establishes a unique relationship between the variables. If there are two variables y and x, and you find that they behave in a certain fashion, discovering the relationship between the variables is actually the business of regression. So this is a distinction that should be kept in mind, and more importantly, correlation and regression are both used in the context of forecasting in various ways. So we will see in a short while how they are used. For instance, if the relationship between two variables x and y is plotted on a diagram known as the scatter diagram, you would find, for instance, in the first graph here, generally as the one variable increases, the other variable also tends to increase. So this is said to be a situation where the correlation is positive. So the correlation coefficient between the two variables would be positive when it shows a trend of this nature. On the other hand, when the relationship of this nature, that is when one particular variable increases and the other variable decreases, then the correlation coefficient is said to be negative, and a negative correlation therefore really means that as one variable increases, the other decreases. That is the physical significance of the correlation coefficient. When these variables are sort of randomly distributed, the way we have in this third diagram, the implication is that there is no correlation between them, they are totally uncorrelated, and this would mean that the correlation coefficient is 0. And what can also happen is that the variables could establish some kind of non-linear association, which would essentially mean that at different points the correlation coefficient would vary from positive to negative depending upon how the situation is. The most commonly used correlation coefficient is the Pearson's correlation coefficient R, which is measured by this particular formula, which says if there are n data points and you have the series x and y defined on these n points, then 1 upon n sum of x minus x bar into y minus y bar, the summation of this expression over all the n points divided by sigma x and sigma y is actually defined as the correlation coefficient. And this is needed in a number of applications where we are expected to calculate the correlation coefficient. And the numerator, in fact the numerator, which is this expression 1 by n sum of x minus x bar into y minus y bar, is generally defined as the covariance between x and y. So covariance divided by the sigma x and sigma y will actually give you the correlation coefficient, and this is how it is. There are various ways of computing the correlation coefficient between the two series. One of the methods is a direct computations using the formula we have just defined. This is generally a cumbersome and lengthy method for purposes of computation. One can also use a shortcut or the UV method, which is basically like shifting the origin, and it involves any conveniently assumed mean and then suitable scaling of variables. So this is generally pretty easy for purposes of computation. For instance, if you have these two series, let us say x is the advertisement expenditure in 10 years that a company puts in, and y is the sales figures over 10 years in lakhs of rupees, which are shown here. So we are trying to find out whether there is any relationship between the advertisement expenditure and the sales, right? So we want to find out, let us say, the correlation coefficient between these two variables. So what you can easily do is, if you want to use the simpler procedure, you can take, for instance, any value corresponding to x minus x bar, y minus y bar, and then get these particular values. For instance, what we have done here is, if we assume that this is 1, then these values will be minus 9, minus 9, this value would be 11 in terms of x minus x bar, these particular values, and similar values would be there for y minus y bar. Having computed the small x and the small y, you can calculate this series x square y square in the form of a table like this, compute the value of xy and get the totals at the bottom of these particular things. And once you do that, you can know, for instance, that x bar is simply 290 by 10, which comes from the values that we had computed at the bottom. Similarly, value for y bar, and this particular coefficient, which is the correlation coefficient, is defined as summation xy divided by summation x square into summation y square under the root, and these values are now available at the bottom of the table. Very conveniently, you can get 0.976, and therefore the coefficient of determination, which is the square of the correlation coefficient, will be 0.953. So this was just to illustrate that the computation for the correlation coefficient and the coefficient of determination can in fact be done in a very simple way. After this, let's come to regression. Regression is the methodology that is quite often used, for instance, in trend extrapolation and causal models, for defining a function which can be used for purposes of making forecasts of demand. So essentially, if we try to ask ourselves this question as to what is regression, basically the purpose of regression is discovering how a dependent variable y is related to one or more independent variables x or x1, x2, x3 and so on up to xn. So essentially, from the demand history, which is the demand as a function of time that might be available with us or with y as a function of x in general, we are trying to determine a relationship of the dependent variable y as a function of the independent variable x. I think it's important to know how you define your dependent and independent variables. The dependent variable is generally the variable that you are interested in, that is the demand, and the independent variables are the inputs that you have available at based upon whatever data is available. Generally that's how it is. In fitting a function, the question that arises very naturally is, what is the criterion for best fit? In fact, a number of criteria have been suggested for fitting this particular function that we are talking about. You see, whenever you fit a function y is equal to fx, what would happen is, this is a plot of the function. Some points will be above the function, some points will be below the function invariably, and this is a positive error, this is a negative error in that sense. So really speaking, you would like to ensure that there are no errors. In fact, if you could develop a function which passes through all these points without any errors, that would in fact be errorless regression function. But what happens is that normally, since that is not possible, we try to develop a criterion which is based on these error functions. So one of the criterion that has been used is the mean error. That means you calculate the error here, some positive errors, some negative errors, and ultimately calculate the mean, and you are interested in minimizing the mean error. Clearly this is not a very good criterion, because why is it not a good criterion? It's not a good criterion because, for instance, if there are 2 points on opposite sides, no matter whether the error is 20 plus minus 20 or whether the error is plus minus 100, both of them would be rated equally by this criterion, and therefore you would like to have a criterion which measures the degree of fit to a better extent. Another criterion is the mean absolute error or the mean absolute deviation, sometimes known as MAD. The mean absolute deviation, your objective function is take the modulus of this, the modulus of this, the modulus of this. So everywhere you get a positive contribution from each point, and then you take the sum. So that's the mean absolute error, which is the sum of the modulus values of all the errors, and you treat that as a criterion. The major defect with this criterion is, what's the major defect with this criterion? What do you think would be the major defect with this criterion? Obviously, the major defect with this criterion is that first you are dealing with the modulus function. Now the modulus function is not a mathematically well behaved function, isn't it? You can't integrate it, it has a cusp at that particular point, right? And therefore you cannot perform all the mathematical operations of taking the derivative and equating the derivatives to 0 and things of that type. Therefore this is not a popular. The third criterion, which is most commonly used in fact, is to try to minimize the sum of the squares of the errors. Each error you square, so if it is negative it becomes positive, that's one thing, and the sum of the squares is a well defined mathematical function which can be utilized for you can use the methods of classical calculus to determine the maximum or the minimum in such situations. Therefore this is done. Moreover, squaring the error is like magnifying the error to some extent. If the error is 2, by squaring it you are 4, so you are focusing on the error, and your objective function is now the sum of the squares of the errors, and it is this sum of the squares that you try to minimize. So it is for this reason that this is generally the most commonly used criterion for determining the correlation coefficient. So as we said, the least squares criterion, that is minimizing the sum of the squares of the errors, is the generally preferred criterion for reasons that we have just discussed. Let's start with the simplest possible situation. Suppose you are interested in fitting a straight line that is the forecast at time t is equal to a plus bt, is the equation of the line to be fitted. Ft is the fitted function or the forecast for time t, dt is the actual demand for period t which is available, past data is available let us say for n periods, and parameters a and b have to be estimated from the data using least squares criterion. That is in fact the problem. So what can be done in such a situation is simply to develop our objective function, which is the sum of the squares of the errors. The sum of the squares of the errors is nothing but the actual demand dt minus the forecast ft whole squared and summed up over all the data points. And since our forecasting function ft is a plus bt, when you substitute it here you get this value, and now the sum of the squares of the errors is our objective function which we want to minimize, and the two unknowns in this particular equation are the two unknown parameters a and b. So you take the partial derivatives of the sum of the squares of the errors with respect to a with respect to b, and you get in fact 2 into dt minus a minus bt into minus 1 is equal to 0, and 2 into dt minus a into bt into minus t, which is the coefficient of et, is equal to 0. And what do you find if we rearrange these equations such that the coefficients of a and b are here, right? A coefficient is simply, in this particular situation it will be simply n, because this is summed up over n and 2 cancels out, and the coefficient of b is simply going to be summation t, and summation dt would come up on this particular side here that we are trying to talk about. And similarly a into summation t plus b into summation t square is equal to summation t into summation dt. Now this is an important equation, that is why it is boxed. And what do you notice in this equation? There are two unknown parameters a and b, so it gives the relationship between these two unknown parameters. Everything else is available from the data, right? So we have got two linear equations in two unknowns, the two unknowns being a and b, so you can solve them by Cramer's rule or any other method for solving linear equations. In fact, the equations obtained from the sum of squares of errors, taking derivatives, putting it equal to 0, these equations are generally called the least squares normal equations. And the point to notice is that the least squares normal equations are all linear equations here, right? In fact, when we use regression as a method for forecasting, the type of regression is generally characterized by the type of least squares normal equations. If the least squares normal equations are linear the way they are here, the method is called linear regression. You will find that even if I had a function like a plus bt plus ct square, which will be a quadratic equation, when you develop the least squares normal equations, we would again get three equations between a, b and c, and those equations will still be linear. Of course these terms summation t cube etc will appear, but it would still be linear. Therefore even fitting a function of the type a plus bt plus ct square is also a problem of linear regression, although the function is non-linear. Okay, this in fact is something that beginners find difficult to digest, because they say that if you are dealing with a non-linear function, how can it be linear regression? So it is linear regression primarily because of the linearity of the least squares normal equations. I think this point must be understood.
So how do we decide that we will use a line as a fit or a quadratic curve as a fit? So how do we decide?
That's your choice, right? That's your choice. You have to make the choice judiciously, and making the choice judiciously simply means that you can look at the data and see which would be the kind of function that will appear. You can try different guesses, and once you have made different guesses, we will have an objective function or the sum of squares of errors which will tell us which fit is better. Okay, so that's the normal way. So a characteristic about the least squares normal equations: these are two linear simultaneous equations in two unknowns, parameters a and b, which can be solved by any of the well-known methods such as Cramer's rule. Equations are called least squares normal equations. For instance, if you look at the structure of these equations, you will find that there is a very easy way of determining a solution for practical purposes. See, these were the equations a, and these are the coefficients. These are a and b are our variables, the unknown parameters, and we had these coefficients and so on. So what happens is, if we use Cramer's rule, for instance, we would have nothing but in the denominator we will have this determinant n summation t summation t square, and this would appear in the values of both a and b. And as far as the numerator is concerned, you will simply substitute this column in this equation. For instance, for a, you substitute for this summation dt summation t dt, and similarly for b, you simply substitute this value in the second column here, and you get the values of a and b after a bit of simplification. So if you want to fit a straight line in general, what you notice from this expression is that you would require the values of these particular things. That is, you would require summation dt, you would require n, you would require summation t, you would require summation t square, and you would require summation t dt. And then by plugging in these values, you can easily get the values of a and b. Now what you can easily do is, based upon these requirements, you can, for instance, organize your computations. And the organizing of the computations means make a table, which means this is Ti, which is your time, this is the demand, which is the data available to you in general. So this is, just multiply these two columns, you will get Ti di, and then square this column, you will get Ti square, and then at the end you can sum them up, so you get these four totals which you are interested in. This is summation Ti, summation di, summation Ti di, and summation Ti square. And once you have these computations available, you can directly obtain the values of a and b by using the formulas which we just derived. There are some computational simplifications in these calculations. By choosing an origin and a scale of data such that summation t is 0, the values of the parameters become very simple. A is equal to summation dt by n, which is the average demand, and b, the other parameter, is summation t dt divided by summation t square. So this is useful for equally spaced data with even or odd number of data points, because you can always choose an origin. If you have, for instance, an even number of points, what would you do? You can take one point as -1, the next one can be +1, and then since the difference is 2, subsequent points can be -3, -5, -7, so that this condition is satisfied. On the other hand, if you have an odd number of points, the middle value could be taken as 0 and ±1, so 1 is the scale factor, and then this ensures this condition, and therefore it's very easy to find out. Let's take an example. Suppose we have the demand of a company from January to December, and this is the actual demand in units sold for the company during January to December. And suppose we want to fit a regression equation, let's say to begin with a straight line on this particular function. So by using the methods that we just indicated, you would find that the regression equation is a straight line whose equation in this case is ft is equal to 193 plus 3t, and the actual demand data is actually fluctuating above and below this particular line as shown here. And then you can use this particular equation to forecast, let us say, the demand for next January. How do you forecast the demand for next January? You will take t is equal to 13, because this is the 13th period, plug it into this formula, and the value that you get is 232. So you make a forecast for next January as 232. And what can we do is, from the errors we can also estimate the standard error of estimate, and find out the range in which the forecast will lie. The standard error of estimate for this example, demand minus forecast, is the error. So sum of the squares of the errors divided by n minus f, where f is the number of degrees of freedom lost, which is equal to 2 because two parameters a and b were estimated. So this comes out to be approximately 7. So if we want the 95% confidence limits of the forecast for the next January, it will be 232 plus minus 14, which is 2 sigma limits. And therefore the interesting thing is that you can get from regression not only the expected demand for next January, but also get that, make a statement saying that there are 95% chances that the demand for next January will lie between 218 and 246, and the demand is 232. That is the interpretation. Regression could be applied to a variety of functions. We have just seen the application of regression to a straight line situation, and for a straight line, let us say if d dash t is the forecast and dt is the actual demand. Basically our equation was d dash t is equal to a plus bt, and there were two parameters a and b which we estimated the way we did using least squares regression, and you will be able to get a straight line. So this was what was done. We might, on the other hand, look at cyclic demand or seasonal demand. This is very common. The demand for woolen garments, the demand for air conditioners, the demand for all seasonal products would be something of a sinusoidal wave like this. So if the periodicity of this particular cycle is capital N or small n, as we have shown here, the equation of this line is d dash t is equal to a plus u cos 2 pi by n into t plus v sin 2 pi by n into t. So if you use this equation in the same manner and compute the least squares normal equations, we can estimate the three parameters a, u and v. There are now three parameters which will be determined again by linear equations. So this is also linear regression, although the function that we are estimating is a cyclic function. Or you might have a situation where the demand is cyclic with growth. That means it has a cycle, but the peak in January 2002 is lower than the peak in January 2003. So there is a pattern of growth also superimposed. So what we do is a plus bt is the component of growth, and this is the periodicity. That is, this is the cyclic component, the sinusoidal component. So u cos 2 pi by n into t, v sin 2 pi by n into t. If you were to use this, you would need to estimate a, b, u and v. These are the four parameters. So in this case you would have four equations which will determine the parameters, the least squares normal equations for this particular case, and the procedure would be similar. Or we might have a situation where the demand is to be represented as a quadratic function, that is d dash t is equal to a plus bt plus ct square. What would happen is that if c is positive, then the demand will take this form. If c is negative, the demand will take this form, okay, physically, and therefore depending upon the data you have available, you can determine the parameters by minimizing the sum of the squares of errors in the usual fashion. So these are some instances of commonly used regression functions which you can now utilize for purposes of determining the appropriate forecasting function. Now, a very common method of forecasting demand is time series analysis using decomposition. So we are next going to be talking about time series analysis using decomposition and see how this particular method of forecasting is actually applied in practice. basic idea behind this particular method is that you know what is a time series. A time series is something, is a function which varies with time, right? So when you're talking about the demand history, in a certain period the sales are 20, next is 25, then they could be 18, then could be 50. So this is a time series, or something that changes with time. It's a general term, right? So what is actually assumed in a time series decomposition method is that every time series that you encounter has these components. It has a trend. Okay, so what is a trend? Generally it is trying to go up or go down, so that's the trend component. Secondly, it might have a seasonality. That means the values might tend to go down and then go up and then go down and go up, so that is the seasonality component of the demand. Seasonality is generally, over a year, over the seasons. You might have a cyclic component. A cyclic component means that there could be a general period of growth and then a depression and so on. So basically here we are talking about large business cycles. So there might be a business cycle, and therefore this could be imposed on the demand. That's another cyclic component. And apart from these, there is always some randomness, which means something going up and down randomly along these cases. So the basic philosophy in time series decomposition is that we try to unearth these components, and once we know the components, we then try to utilize these components to forecast the demand. That's what it is. That means the time series is decomposed into these various components, and then these components are put together. You can forecast the trend separately, you can forecast this, you can forecast this, whatever it is, and then from that forecast you can try to build the demand for the time series. That's the basic idea. The most commonly used method for determining these components is the use of a multiplicative model, although an additive model is also used in some situations, but this is the most popularly used model in time series decomposition. What it says is that the forecast for time period t will be the trend for time period t multiplied with the seasonality component for time period t multiplied with the cyclic component at time period t multiplied with the random component for time period t. So you have to actually get these components, and these components will also be functions of time, and once you can put them together. So the basic philosophy is that if this is the time series which is generally going at a particular time t, if you want to find out, you have to identify these things: the trend, the seasonality, the cycle, and the randomness. Having obtained these components, you can put them together and use this formula and obtain xt. That's what it is in the multiplicative model. Okay. Now how it's done is something that we'll see shortly. A very important concept in the development of the time series decomposition is the notion of what they call deseasonalizing the time series. So the basic concept is that if the time series represents a seasonal pattern of L periods, then by taking a moving average MT of L periods, we would get the mean value for the year. I think this is obvious. For instance, if there are 4 seasons, what it is, 4 seasons, so each season is of 3 months duration, right? So if we take the demand average for 3 successive periods, that would in fact be the average demand over these various periods. That's what we are trying to say. So what it means in general is that if you reckon that the periodicity of or the moving and the seasonal pattern is of L period, seasonality pattern, then you take a moving average of L periods and we would get the mean value of the year, and this would be free of seasonality and contain little randomness. Why? Because of averaging. Averaging always tends to reduce the randomness, and therefore the moving average at time t will be the product of the trend and the cyclic component. That's what it is, right? So because we have taken care of the other factors, then this was determination of de-seasonalizing the demand, means getting rid of the seasonal effect. How do you get rid of the seasonal effect? By taking a moving average of the requisite number of periods. So you get rid of that. If you were to now determine the trend, how will you determine the trend? You take the de-seasonalized series which we have just determined. A suitable trend line could be fitted using regression. So you use regression again, right? And the choices could be very simple choices. It could be linear, quadratic, exponential, or other functions, whichever function that you want to see. So once you have a de-seasonalized series, which is like the average, how it is behaving, you try to find out what would be the best function that would fit this. This can be determined by regression or it can be determined by inspection, depending upon what is the degree of accuracy you want, and that function will be the trend line, TT, that we are talking about. Then how do you determine the cycle component? After the trend TT has been estimated, one can use CT is equal to MT by TT. This is the moving average. The moving average was the product of the trend and the cyclic component, and therefore to determine the cyclic component you can simply divide the moving average by the trend, and this will give you the cyclic component. This is the idea. And what remains now, we have talked about the three elements, the major elements here. What remains is the how exactly do you determine the so-called seasonality factor or the seasonality indices in this particular situation. So to isolate seasonality, one could simply divide the original series by the moving average, because the moving average is an average and everything will be above or below it. So this ratio xt by mt will be nothing but, this is xt, the whole thing, tt, st, tt, rt, divided by mt, which is tt, ct, and basically what you find here is that by dividing this original value by the moving average you get the seasonality multiplied with the random factor. That's what it is. So averaging over same months eliminates randomness to some extent. So this way we get the seasonality factor only. That means dividing the series by the moving average, we in fact get the seasonality factors, and these are generally known as seasonality indices. Okay. So we have basically seen the procedure that will be applied to determine seasonality, and then this can be done through dividing the original series by the moving average or the moving average of L periods, then identifying the underlying trend, which can be through regression, and the seasonality indices. And now that we have got these components, we can put them together and get the entire forecast. So the basic procedure for time series decomposition can be summarized as these two steps. One is that you decompose the time series into the components, that is, first find the seasonal component, then de-seasonalize the demand, and then find the trend, because once you de-seasonalize, it is the series from which you can find out the trend, right? And then utilizing this information you forecast the future values of each component, which are these components, and then you project the trend component into the future, multiply the trend component by the seasonality component, and this will basically give you the forecast for the next period. So this is essentially time series decomposition, which goes in this particular fashion. So this was basically an overview of the procedure. What we will do now is to take 3 progressive examples to illustrate how the procedure will be applied. So these examples will start from a relatively simple example to a more complicated example to a relatively real life example of how the procedure for decomposition is going to be applied, so that you get an appreciation of this particular method. What we can do is, let's take the first example. The first example is, suppose demand is available to us for the last year and the past sales for different quarters are: during the spring quarter it was 200, during the summer quarter it was 350, during the fall quarter it was 300, and during the winter it was 150. Suppose this demand is available. So this is data that is available. From this data, let's see how we can compute the seasonality factor in this particular situation. You can see that the total demand over the year is the sum of all these values, which is 1000, right? So that now the average demand for each of these quarters divided by 4, 1000 divided by 4, because there are 4 quarters. So average demand for each of these 4 quarters is 250, 250, 250, 250. So the basic idea is that the average demand was 250 in each quarter, yet in each quarter the demand was actually fluctuating above or below it. So what you can do is actual demand divided by the average, right? 200 divided by 250 is actually 0.8. So this becomes the seasonality factor for spring. What it shows is that on the average the demand during spring was 80% of the average demand. That's what it shows, nothing else. Okay. Similarly, during summer the seasonality factor was 350 divided by 250, which is 1.4, and this is 1.2, and this is 0.6 similarly. So these are now our seasonality factors, which show that in different seasons, during spring it is 80% of the average, during summer the sales are 140% of the average, during fall 120% of the average, and during winter just 60% of the average. So these are the factors. So now we have identified the seasonal factor for this particular example. Then let's say we want to make a forecast using this seasonal factor. How do we do it? What we can say is that last year our demand was 1000. We expect that next year it will go up by 10%. So let's say that the expected next year demand is a total of 1100. This could actually be developed by regression or any other technique, but we are just trying to identify how exactly we'll put the components together. So we say that the total demand for next year is likely to be 1100, which means that the average sales during the period for the next year are likely to be 1100 divided by 4, so 275. This is the average for next year. What we now do is we assume that the seasonality factors that we have computed in the last year will continue to operate in the next year. So for the spring season it was 0.8, 1.4, 1.2 and 6. So we utilize the seasonal factors there, multiply this and you get the next year's forecast. So this is the intention. The intention was to obtain a forecast for next year. So we know that the demand for spring is likely to be 220, the demand for summer is likely to be 385, this is likely to be 330, and this is likely to be 165. So this was a very simple example to basically give you an understanding of the use of seasonal factors and the average demand, which is the basic trend. So that we assumed rose by 10%, right? Let's take a slightly more complicated example. Let's say that we want to compute the trend and the seasonal factor on a 2-year demand history. Okay, which means we have data for 2 years. This is the first quarter of the year 2000. So demand is 300, 200, 220, 530, and then 520, 420, 400 and 700. So this is actually the demand data available to us for the past 2 years. So how do we get the factors from this particular situation? What we do is, we have these 4 data points for 2000, these 4 data points or these 4 seasons for 2001, and the demand is 300, 200, 220, 530 and so on. To this data which is there, we fit a regression line. Okay, to these 8 points we fit a regression line, and the fitted regression line is trend of these points, which is 170 plus 55t. So we establish the trend equation from to these points and we get this, and from this trend equation we can actually calculate what the demand would be. For instance, if you take t is equal to 1, this would be 225, t is equal to 2, it will be 280, etc., etc., etc. So these are the values that you get from the underlying trend, from the regression line. Then what we can do is, we are interested in finding out the seasonality factors. What you do is, you take the actual to the trend. This is the actual that you have. Actual is 300 divided by 225 is 1.33, and 0.71, 0.66, 1.36, that is for the first year. When you do this analysis for the second year, this will be 520 by 445, which is 1.17, 0.84, 0.72, 1.15. Now these are different, right? So what you do is, to calculate the seasonality factor for the 2-year horizon, we take the average of this. That means 1.33 and this particular value of 1.17, the average of this is 1.25, and then this is 0.78, this is 0.69, this is 1.25. So what we have ultimately established is the seasonality factors for each of the quarters. So the first quarter, second quarter, third quarter, fourth quarter, and also this applies in each year. Now we can use this information to develop a forecast. So forecast for 2002, that is the next year, using trend and seasonality factor would be, we use the trend line 170 plus 55 into the 9th period, the 10th period, 11th period, 12th period, whatever it is, multiplied with the seasonality factors which we have just computed, 1.25, 1.78, 0.69, 1.25, and this becomes therefore your forecast for the next 4 quarters of 2002, which takes into consideration trend and seasonality in general sense. Okay, this is the method that you would adopt for, understanding of both. First we talked in the first example mainly about seasonality. Here we talked about both trend and seasonality. Let's take a third example, and in which, let's say we have a given demand history, we want to prepare a forecast using decomposition. How do we do it in general? These are the 8 periods, 1, 2, 3, 4, like first year and the second year. This is the actual demand which is available to us. What we do in this particular situation, we again have the actual demand over 8 periods. So the total demand is this, and therefore this is the average demand. 679 is the average demand here. So then what we do is, we calculate the period average. What is the period average? The first period in the first year and the corresponding first period in the second year. So take the average of 300 and 416. This becomes the period average, which is 358, 650, 1038 and so on. And this is just for 4 periods. So the total will be half, 2716, and the overall average for this is 679. We have constructed the same. Then you can find out exactly the seasonality factors. What would be the seasonality factor? The seasonality factor would in fact in this particular situation be this particular value divided by the average. So 358 divided by 679, 650 divided by 679 is 0.957. This value divided by 679 is more than 1, which is 1.529, and then 670 by this is 0.987. And the way we have defined it, because we have calculated these period averages, these factors will repeat themselves for the next year, right? And therefore, having got this seasonality factor, we can get the deseasonalized demand. How do you get the deseasonalized demand? You have to actually take out the actual divided by the seasonality factor that you have. So 300 divided by 0.527, you get this particular value, and similarly you get these values which are now deseasonalized demands. Then from the deseasonalized demand, we have to identify the trend. So to the deseasonalized demand, you fit the regression equation. So these are the values. This is the deseasonalized demand, sums, averages, y, this is the y, this is x square, xy, and so on, and you follow the routine procedure of fitting a straight line, and ultimately for this straight line you get the two coefficients a and b, and the values of a and b are: b is 39.64, which is the slope of the straight line, a is 500.6. so this is the equation of the deseasonalized regression line, 500.6 plus 39.64. that's what you will do. So using this information, now we can build a forecast. How will you build a forecast? Suppose you are interested in the forecast for the next 4 quarters of the following year, that is period number 9, 10, 11 and 12. So this is the trend forecast which you get from the equation, the regression equation which you have determined, right? 859, 897, etc. The seasonality factors are the ones that you have computed earlier. So you multiply this and this becomes your final forecast. So you get the forecast for the 9th, 10th, 11th and 12th period. And finally, the important thing to note is that to identify random data, or to identify a trend, or to identify seasonal data, especially if you are using Box-Jenkins models, you need procedures to identify what kind of a trend is. So what can be done is that we make use of what is known as autocorrelation. That means you take the correlation of that particular series. If you displace the series by 1 period and you find out the correlation between the two series, you have autocorrelation of 1 lag, autocorrelation at 2 lag and so on. So this is the autocorrelations, which is nothing but the correlation coefficient computed by displacing the series by 1 or 2 or 3. So if it is random data, what is shown is that the correlation coefficients generally tend to be small and going randomly up and down in the line. If there is a trend between operating within the forecasts within the time series, then it is generally found that the autocorrelation coefficients tend to have this lag. If it's seasonal, the autocorrelations also determine some kind of seasonality, and the autocorrelations are in the range of -1 to 1, which are plotted on the x-axis. So this kind of a plot is generally very useful to identify the kind of relationship that exists within the time series as to whether it is random or trend or seasonal. Okay, so it's more like trying to say that if you examine a patient's blood and identify different tests on it, the different tests will actually show you the presence of different kinds of diseases. So in the same way, if you take that example, if you look at a time series and calculate the autocorrelations in some way, the nature of the correlations will tell you whether it is this or this or this. So this becomes a systematic approach to basically handle some of these essential questions. So let us try to see some of the major conclusions that we can derive from what we have talked about today. First thing that must be kept in mind is that we have talked about a number of different forecasting procedures. We have talked about regression, we have talked about time series decomposition and so on. So the question that is paramount is, how do you choose the right forecasting technique? So the right forecasting technique is dependent to a large extent on the problem context, on the accuracy you desire, on the cost that you are willing to incur, and on the planning horizon which exists for you. For instance, regression would be an appropriate technique if you are assured that the kind of chance causes which operated in the past will continue to operate in the future, and under that system whatever was happening you could extend it into the future, so it would be a good technique. But if this is not happening and the time series is behaving in some erratic fashion, then time series decomposition for an arbitrary time series could be a good way, because you determine the seasonality coefficients, you determine the underlying trend, you determine the underlying cycle, and utilize this information for making a forecast. So in that sense, the importance of correlation and regression in the analysis of time series was emphasized. The least squares normal equations with examples were illustrated so that you know how to estimate the parameters, which is the basic operation required in regression. And then we talked about time series decomposition, where the various components of the time series like the trend, the seasonality, the cycle and the randomness were identified and considered separately, and then from this you could build the whole thing. This building was done by first deseasonalizing the demand, that means ripping the demand of any seasonality, and it was to that deseasonalized demand that you actually fitted some regression data or some straight line or whatever, so that you can construct the time series, and then you went about with the process of reconstruction of the time series by putting the coefficients or the components together. We also saw 3 illustrative examples of time series decomposition, which were designed basically to add progressive stages of difficulty so that you could get an appreciation of what is the concept of seasonality, trend, cycle and so on, and they could be used. And finally we saw that autocorrelations could be used to identify the kind of time series, and depending upon the behavior of the autocorrelations you could have a random or a trend or a seasonality factor, which could in fact be looking into the various aspects of this. So with this we conclude our discussion on forecasting methods. We have looked at forecasting from the point of view of its importance in planning decisions, and then we have seen various methods of forecasting, subjective and objective, and in today's lecture we have looked at some of the procedures like regression and time series decomposition, which are essentially used, which are objective procedures to develop a time series forecast. And now based upon this analysis we will try to use forecasting for the various planning decisions in a company. So when we start the next lecture we shall be talking about aggregate production planning, where a forecast of demand is available and we see how to plan the operations of a company over the next 6 months or 1 year, as the case may be.